Postsynaptic potentials are changes in memory potential in the postsynaptic neuron. So one neuron again talking to the other, and that's going to change memory potential, which is going to cause that signal to be transmitted from one cell to the next. So let's go back to this picture that I drew you in the previous lecture, where we have a presynaptic neuron releasing neurotransmitter chemical messengers into the synaptic cleft, where a postsynaptic neuron is going to be able to receive those signals. We're going to focus right now only on ionotropic receptors, that direct effect, just to simplify things. So we've got this chemically gated ion channel, and it is going to open in response to this stimulus. Let's write down what the specifics, which I already did in the previous video, but let's do a little bit more here. So we're going to open ion channels. What type of channels? We can have sodium. Sodium will flow in. Down its electrochemical gradient. What is this going to do to the cell? Depolarize the cell, more positive inside the cell. If we have a potassium channel open, which way is it going to go? Flows out. Positive flowing out is going to hyperpolarize the cell. Chloride. If we have that, those channels open, it's going to flow in. There's more chloride outside the cell than inside the cell. Even though it's negative inside, there's still, and so now I'm telling you, if you didn't know, it goes in. That's down its electrochemical gradient when you start at rest at -70. So this is going to hyperpolarize. Now, I'm going to introduce one more set of terms here that we will review again. So let's review here. We're going to have some excitatory signals. So depolarization, that's going to be excitatory. It's going to bring the cell closer to threshold. So this one, give myself room here, is called an excitatory postsynaptic potential. EPSP. Fun name, right? Then we've got some inhibitory signals here. Hyperpolarizing the cell brings it further away from threshold. These are inhibitory. These are inhibitory postsynaptic potentials. And again, these are postsynaptic potentials are graded potentials. They are local. They can be different sizes. They can summate or add together or take away from each other to become action potentials, but they don't always become an action potential. Okay, let's go to what this looks like in terms of changes in membrane potential. So what I'm going to have you do here is make me smaller. And I want you to draw a graph showing the changes in membrane potential due to the movement of ions over time. First, the release of glutamate, then the release of GABA. Label these different components: hyperpolarization, depolarization, and repolarization. If you need a reminder, I could tell you this neurotransmitter is going to bind to receptors and open which channels? Na plus / Ca channels. GABA is going to open chloride channels. So please pause the video to be able to draw this out. Okay, I will try to do it here. Actually, I won't. I'm going to take you to the next slide where I have it in a nice schematic for you. So here we go. This is us answering this question here. We've got resting membrane potential is where we start at -70. You should have started there. When glutamate is released, sodium and calcium are going to flow into the cell and cause depolarization. That's right here. Once glutamate is removed, we have repolarization. That's it. Then for GABA, we've got GABA released. That's going to cause the cell to become more negative because chloride is flowing into the cell. And then when GABA is removed, we go back to rest. Why? Because that neurotransmitter signal was terminated via those mechanisms I showed you before. Now, what are these called? These are called EPSPs and IPSPs. Notice None of these are action potentials. It's just changes in membrane potential. Where are we, actually? Where does this happen? This happens at either the dendrites or cell body. This does not happen at the axon, ever. Changes in membrane potential at the axon are action potentials. So this is happening here. Graded potentials are postsynaptic potentials. We started with those, now we're ending with them again. So go back to that if you need to. Remember, the graded potentials can be hyperpolarizing or depolarizing, depending on what kind of channel is open. I told you that like 10 videos ago. So the axon itself is not stimulated. These incoming signals are at the dendrites or cell body. How do we get an action potential? These sum together to reach threshold. Threshold about -50, -55. These have to reach threshold. So let's look at what that looks like. Moving on here. Here is a kind of schematic of incoming signals that would passively spread. Maybe that, remember, that's a characteristic of graded potentials. So these incoming IPSPs and EPSPs are going to passively spread. They may or may not reach the axon hillock, meaning those ions, actually the change in membrane potential reaches the axon hillock. Axon hillock is the beginning of the axon where if you reach threshold at this place, an action potential is generated. So if we have enough excitatory signals, in this diagram, it's kind of only showing excitatory signals. If you have enough, you're going to have an action potential. So what this looks like kind of here, I showed this before. If you have one stimulus coming in here, assume excitatory, that might just, the ions are not, it's not enough ion flow for that to reach the trigger zone at the axon hillock. However, if you have two different stimuli, well, now we've got twice as many ions traveling in here. The neuron is going to integrate those two, add them together. The effects of them are going to add together. Even though these both are decremental in terms of the graded potential is decreasing as it moves, it's enough for them to sum together and cause an action potential. So what this looks like is these stimuli can add together in either time or space. Let's look at what I mean by that. Here are two different excitatory inputs and one different inhibitory input onto the cell, presynaptic cells and postsynaptic cell. And we're going to look at some different scenarios about if you have different numbers of these firing, right? What would make this excitatory synapse release would be an action potential down this axon terminal here would cause a release of maybe glutamate. Here, if there's an action potential in this neuron, it would cause a release of glutamate. This neuron, if we have an action potential down this neuron, it would release GABA and be inhibitory. So let's look at these examples. First, we've got just excitatory signal 1 coming in 2 times that are separate in space. Does an action potential occur here? No. Why? We haven't reached threshold. These little blips are graded potentials. They're both excitatory postsynaptic potentials, but they are not enough to reach threshold. These are 2 EPSPs. If these two same input signals happen closer in time, these EPSPs will add together to cross threshold. You can literally think of these two adding on together. So that's temporal summation, summation in time. The next example here is spatial summation. Here's excitatory synapse 1 and 2 that are separate, 2 EPSPs here. But then we've got excitatory synapse 1 and 2, 2 different input signals that are happening at the same time. This is spatial summation. So we've got a signal both from here and from here happening at the same time. Spatial summation across space. Then we can also have cancellation. So these sum together, but if you add in a negative, if you add in an inhibitory, it's going to take away. So here is an EPSP. Here is an IPSP. Each of those are kind of independent. In this place here, we've got summation of an EPSP and an IPSP that basically cancel out. It's not always going to be completely a flat line, but it's not enough to reach threshold. And you can have all kinds of scenarios like this, right? You could have 2 of these at the same time as 1 of these. Would that be enough? Okay, in reality, there's not just 3 incoming signals. How many are there? Whoa. These are all synaptic terminals, shown in blue here. The cell body of a neuron, which is kind of the purple underneath here, is covered in axon terminals with synaptic clefts in between here where neurotransmitter is released, either excitatory or inhibitory neurotransmitters. There's also glial processes, other things shown here. All the blue are axon terminals. So because it's literally covered with synapses, each neuron receives input from thousands of other neurons. This image here is the same idea. All of this yellow are incoming signals on the dendrites of this multipolar neuron. So because of this, we've got an adding together of excitatory or inhibitory incoming signals, which result in depolarization or hyperpolarizations. And then the neuron is integrating all this information received along the dendrites and cell body that all are coming in at a single time, across time. It's crazy. And then the axon hillock is where an action potential is generated if the net polarization reaches threshold, if it becomes sufficiently depolarized to pass that information on to other neurons. So it's an integrator, right? This is an example of the nervous system being an integrator, a control region. And why does an action potential generate here? That's where there's voltage-gated sodium channels, period. Okay, so this is that all or none phenomenon that occurs right here if we've got a large enough signal. So what we've got here is the integration of synaptic inputs is the sum of all EPSPs minus the sum of all IPSPs at any given moment in time and potentially over time if you have temporal summation. This is both the number of them and the size of them, because remember EPSPs can be graded, meaning they can be different sizes, unlike an action potential, which is only one size. It's all or nothing.